con una emergencia y no accedí a la programación. No sé si me pueden apoyar en esta ocasión debido a que tuve que salir de emergencia de la casa.
Perfecto, doctora. No se preocupe. Adelante, doctora, voy a apagar la presentación.
Ok, gracias. Bueno, en este momento vamos a continuar porque no paramos, porque en el otro lado después de cruzar el charco estamos en el otro lado, entonces ahí están en otro horario y es necesario que avancen ya. Tenemos en este momento el mini curso de computación científica con Python, ¿no? Así es que, no sé si está ahí Estefan, queremos continuar con este mini curso y en todo caso también la responsable Vanessa Nittel, que están también responsables de este curso y que le está pues presentándole desde el nivel bajo para que pues terminemos manejando este lenguaje que es muy versátil en este tiempo y espero que lo aprovechen. Adelante, Vanessa.
Thank you very much. Muchas gracias. So I will switch back to English now for the course. First of all, sorry for the inconvenience last Saturday. Like last half hour, my internet was down and I could not reconnect. I think Stefan was there. I texted him from my phone and I hope he told everyone that there was a problem. Yeah, I hope today everything will be all right. So sorry again for the inconvenience. Okay, I sent the material from last time. I sent an email to the list of participants with a link to a cloud. So you should be able to see all the material in this folder. And it is available until end of September. And all the new material I will put there as well. So then I will go into screen share now. You should be able to see the Jupyter notebook again. And we just recapitulate where we were last time. I think we unfortunately dropped out quite quickly when we were discussing the solution to task 3. So maybe we just repeat this to be like in the material back again, and then we proceed, do the rest of last Saturday, and then we start with Numpy and plotting and the modeling, pandemic modeling. That's what we're up today. Okay, to recapitulate, again, task 3. I think the first one we already discussed. You were to implement a function with 2 lists, taken as arguments, and to create a third list that should contain only odd numbers from the first and even numbers from the second list. You can do this with list comprehension, for example. Let's check the solution. One possible solution, of course, there are many more. You come up with 2 Python lists and a definition called merge list is my function here now. It takes 2 lists as input and creates a new one. Therefore, you start with an empty list. You can also use list and round brackets. And then you just do one list after the other with 2 for loops. You can take all the numbers from the first list, check if they are odd, and if so, then you append to the result list. After you have done that, you proceed in the exact same way with the second list. When the elements in the second list are even, then you append, and in the end, you return the list that was appended step by step with first odd and then even numbers. We can run the script and see if it works. So here we have, first we have the odd numbers from list 1. Let's check. Yeah, 23, 11, 17 are the odd numbers, and then 24, 36, 12 are the even numbers from the second list. Way shorter is the version where you use list comprehension. Again, we have a definition here. We take two lists as input arguments, and we return directly the result list, and we use list comprehension. Again, separately for the two lists, and you can just add one list to the other. Adding here means that you append. So this plus here for list is a concat. This works also if you have two lists of strings, for example. Then it's just a concatenation. It's not a plus like an addition in mathematics. And the first part again is like in set comprehension. You define all the numbers x for which holds true. Then x is from list 1, and also you want that x is in this case odd. Then it's in the first list. And then the second list, you do the same. You just switch to even numbers here. Reminder, this is modulo operator. So basically by %2, we check if it's divisible by 2 when testing if it equals 0. So this is the two versions, and you see the list comprehension is great. Mathematicians usually love it. It's a one-liner basically. And if you do it with separate for loops, it's a lot of lines, let alone for the indentation that you need. So remind you to take the list comprehension. Okay, then the second task. You were to come up with two ways to calculate the squares of a list of elements. And first you were to do this element-wise, and in the second step, come up with a function that accepts a complete list. You can use the map method, map function from Python. Let's check the possible solution. So first, element-wise, we can define a function that is named square element, and it directly returns the power of 2 of the given argument. So you enter just one number and get the power to 2. If you want this done element-wise for all the elements in the list, you use the map function. For example, I took list 1, that was a list up here with these numbers. The map function now takes a function, that's the one defined here, and puts in everything that's in the list here. So basically, it means we evaluate the function square element for all the elements given in this list. You can think of this as a set of numbers, a mathematical set, and you want the function to be evaluated for all elements in the set. This is what map does. And if you want this as a one-liner, you can alternatively use a lambda function instead of a function definition. So instead of square element, I can use the lambda function. The lambda keyword tells us, okay, this is a function coming. The variable is x. And after the double point, you tell the function what to do. In this case, again, square everything. And then put the lambda function and the list of interest into map. Let's run it and check. So here are the outputs for the two versions, and we see it's the same result. It is the squares of 10, 20, and so on, what was in the first list. So also lambda functions are great to shorten your code. And then the second part of the task was to write a function that takes a complete list as input and works on the list and not only on one element. So square list is a function definition that takes an input list that is not typed, right? So the function doesn't know that it has to receive list, and it doesn't check this. So in this case, you as a user have to check that you enter only correct things. Again, it works with list comprehension. It directly returns the square for all the elements from the input list. Again, just as you would write down a set comprehension in the exact same way, basically, just add a for and an in instead of element sign, for example. And you see the result, that's the third line. Again, you receive the same result as for the other options. So always try to use the set comprehension. It usually helps to make things shorter. So we will finish now the basics and then move on to Numpy. There is 3 more things that we do today here in the basics. The first thing is we talk about classes real quick because we don't have so much time. But classes are a nice thing if you want to use Python for a bit bigger programs, or also if you reuse typical things very often. So far, we basically learned about procedural programming, meaning that you do one command after the other and your program follows stepwise, one command, next command, maybe it goes back if you add a loop, something like this, but it does it in a procedural way. And we also had a look into functional programming. We used functions. This is very normal for mathematicians. They deal with functions all the time. And the third typical type of programming is object-oriented programming. And classes are the most important structure in object-oriented programming. You can think of a class as the idea of a thing. For example, we can think of points as an idea. A point is given by 2 coordinates in this case. Let's say we are in 2-dimensional space. A point has 2 coordinates, an x and a y coordinate. In this class, you can have explicit instances of points. I can put one point here and one point somewhere else. This would be an instance. So then we have really 2 objects, 2 different points. And what I have in common is both of them are points. They are described in the same way with 2 coordinates, and maybe the same things can happen to them. For example, with points, we can calculate the distance between 2 points. We can translate them maybe. So a point is defined by the things that it contains and also by the things that you can do to it. So we define now a class as an example for points, because this doesn't exist in this way in Python. Yeah. So basically we kind of develop a new type. This is our point class. So in the docstring, I write it's a class to represent a point in Cartesian coordinates. And the class always needs some constructor. Again, the class itself is just the idea. And to construct a real point, you need a constructor. This is given by this def init. This makes this name point to be callable. So we can call point now and enter 2 coordinates, x and y. Therefore, you need the self keyword. And we define by calling later point that we create thereby a new point, and we have to give the coordinates. The point needs an x coordinate and a y coordinate. We add this to self. This basically just means that we create the thing now, the instance. And then furthermore, we can define for the total class, meaning for all things of type point, that they should be translatable, for example. You can come up with whatever you want to do to points, but one thing would be we need a method to translate them in 2-dimensional space. Translate them by some distance in x dimension and some distance in y dimension. This is what this method does. So basically it adds the x and the y translation to the x and the y coordinate. Furthermore, with this keyword, and again, you need the underbars, you can basically make it printable. Here you can define what to happen when you use the print command to your new class. So this is what we define now as a class. Let's run it. So Python knows now what a point is. And this is something that we invented now. It wasn't there before. And now I can create a real point. Let's say for a start, I want the origin. So my first point is supposed to be at 0, 0 position. Then I can run the cell and see what happens. And now I have a point at 0, 0. The print was defined here with the string method. And when I call print now, it prints exactly what is returned here. It tells me all the information that is relevant for the point that I just invented. And by calling the class itself, I construct the point, and therefore I have to give the coordinates. So of course, now the idea of the class was that we can have different points, not only one. We have now many options. We can have instances of this class. So for example, in addition to point 1 in the origin, I want another point, a new object. That's why it's called object-oriented programming. This is now a separate object that has the same, basically, type, if you want. So the second point is printable as well, and I already translated the first one, because translation is something that we can do to points now as we defined it. So the whole idea of having classes is that you can basically sum up the similarities of things. So things that want to use the same functions, that they can go to the same class if they are constructed in the same way, and you can apply the same methods. So all points are now together in the point class, and P1 and P2 are two instances of this class. So whenever you want to reuse code and you want to deal with objects of a certain type that is not already a natural type, like matrix, for example, then you can define your own class. That's when you want to do this. And also, when you have done one instance in this class and you do, like, for example, a translation to this instance, then all the other objects of this class are not affected. So only point 1 was translated and point 2 stays wherever it was before. If you want to translate it, you have to apply the method again. Later, when we do the plotting, we will see again how object orientation works. It's probably the newest if you haven't programmed before. The procedural and the functional programming is, as a start, usually easier, but object-oriented programming is super common nowadays. So maybe you want to have a closer look at it. And now you know how to define your first class. Then another helpful thing, if you want to reuse code, is to define your own module. We learned already how to import modules, but sometimes it's useful to write your own. This can be really short. It doesn't have to be like the complete math module with all the functionality. It can be something with only 2 or 3 functions that you reuse all the time, and then you put it in a module and import them every time, and then you don't have to write the full definition again and again. So for example, here I come up with my own module. It's just a tiny one to show you the principle. This is just needed in Jupyter Notebook so that this is saved now in a real file. You can also do this with any editor. You just open a new file, call it whatever you want, for example, my module.py. And there you put everything that you need later in maybe many other programs. So for example, a variable that you want to reuse, that's an important constant that you need all the time. Or a function that you defined and you want to reuse it all the time. Or maybe the point class. Maybe the point class is useful in many of your projects and you put it in your module. And you could name it point module and add whatever you want or is relevant for points. So when you write this into a file, you can now reuse it just in the same way as the official Python modules. You use the import keyword. This works with every .py file. So also with my module. And if you wrote a doc string, you can now check the help of your own module that you've written. Then you directly see what's in there. Apparently a class exists, it's called my class. Apparently this is an example class, and normally some interesting things would come here. Later we will do this, not with the full module, but with a few functions that we maybe want to reuse several times. We do this when we do the pandemic modeling. So when you've imported your module, you can use everything that you want stored there. For example, the variable is still there, your function, you can call it, and also your class is still available. So in my next Jupyter notebook, when I import the module, I can do all these things directly away. Last thing that we do in the basics is the exceptions. It's not very important for a start, but it's helpful if you dig deeper into the material. So exceptions are a way to handle errors. We've seen this sometimes. You have a typo, or you forgot to name a variable in the correct way or so, and then an error is returned. The problem then is that your program stops. If you already know that this might happen, you can catch the error before it happens. So for example, if you are not sure when you load data, if all the data is actually numbers, because it's a huge file and you haven't checked, and you want to do numerical things to these data, so for example, add something, then you will get an error if the data you load is not of the correct type. If you load a string, then it doesn't know what to add. So in order to check this, you can try, for example, to add. And if it doesn't work because it's of the wrong type, then you say, okay, in that case, if it doesn't work, then do something else, please. This is try and accept. So what you do is you try to do something. That's what you actually want to do. And if this is for some reason not possible, then you add an exception. Then you say, okay, if it's not possible, then please at least tell me. If you put something in except, then you won't get an error, but the exception method will tell you something is not okay, and it can even tell you what. So for example, here, I want to print a variable. As a print test means, of course, this is a string, this will work. This just tells me we're in the try case when this is printed. What I actually try is to print a variable. So for example, I want to see what value is stored in some variable named test. But it might happen that this variable doesn't exist. And then normally I would receive an error. And all the rest of the code would stop. If I already know maybe this variable doesn't exist, I can just try to print it. And for example, the exception could be, if it doesn't exist, then now come up with one variable in that name. So if I run this, I will not receive an error because we went to the exception, and this tells me, okay, apparently the print test was not possible. And if you want to know why, you can actually get the error message, but not as an error stopping your program flow, but just as an information. So here you can print now the error message. This is always stored in some variable e. You don't have to define this. This is done internally. So when I run this, I want to try to print the value of some variable. If it's not possible, then please tell me why with the except method. If I run this, then it says, okay, I caught an exception. The variable is not defined. So here the text of the normal error message is printed. And this makes it not an error anymore. So I could proceed with my code. And that's the whole idea of this. I will just quickly check the chat. When I started this, YouTube. As I said, this is not the most important thing for a start, but I wanted to put it in a material so that you can later have a closer look at it when maybe you need it in a bigger program. So basically, this is where we would have ended last time, but then yes, unfortunately, my internet went down. But we finished this now, and we'll now go to the next part. And the next two parts is more for you to do, some more tasks for you, because now we have a lot of the basics. So you have more options to try yourself. So what we do in the next is the is Numpy. But before we start with this, we do a little recapitulation. So this is the first time for today where you are up to do something. And this is work on the task given here. I will stay online. You can try it for yourself and ask questions via the chat, or also send me your solution and I can check on it. This now deals with the things that we learned last Saturday. So first you have to write a function that takes a list of numbers, and it is to remove and print every third element in the list. And you do this in round robin fashion, so over and over again until there's nothing else left in the list. You can check the list methods with help list. So if you're unsure what was going on with the list, check help list, or check the material that I sent you last Saturday and try to come up with a solution. The next task is also to define a function. There you should multiply two given numbers, but only if they're integers. So you have to perform a check. If it's a float or a string, nothing shall happen. Maybe there should, in this case, actually, an error message shall be printed. So multiply two numbers, but only if it's integers. And it's supposed to be a function, so you have to enter the two numbers. The third is to implement a program that takes three lists. And by using the map function and the lambda function, you're supposed to add three lists. Add, in this case, take lists of numbers and add the numbers. So you can put ints in the numbers, integers. And the fourth task is to come up with a function that prints the Fibonacci series. And as an input argument, to take the number up to which value you want to print the series. Because if you don't enter a stop number, then this will go on forever. So print all the Fibonacci numbers that are smaller than n, lesser than n. And if you forgot what the Fibonacci series was, is defined recursively. The first two elements of the series are a 1. And from then on, you calculate the next element by adding the two before. So now you have time to work on these tasks, and I will check. Maybe like 15 minutes should be fine. And if you don't get it all done in 15 minutes, it's not a problem. It's just for you to come back to coding.
Doctora, buenas tardes. ¿Ha concluido con su exposición? Doctora, doctora Vanessa, está concluyendo su exposición, ¿no?
What do you mean, sorry?
Juana Zabaleta, y de la comisión organizadora.
Sorry, I didn't understand the question.
¿Alguien que nos pueda ayudar?
Intervenir para traducirla.
Por favor, le agradezco, le agradezco.
Okay. The question is that if you have already finished your talk.
No. Now this is a task for everyone to do on their own trial.
Ya, dice que todavía no ha terminado, sino que le ha dejado tarea para que todos intenten resolverlo. Así que hay que dejarle espacio de tiempo, ¿ya?
Ok, bien, señores participantes, entonces le damos el tiempo prudencial para que puedan concluir, avanzar con el trabajo. Ok, continuamos entonces en breves minutos.
Sí, déjale nomás tiempo, profesora. Cualquier cosa me puede requerir.
Ok, muchas gracias.
So as it's an interactive class, from time to time, you have to work on the task on your own. It's the only way to learn programming. But only like 15 minutes, and then we have a look at a solution.
Lo que dijo es, como en cualquier clase, se le deja un espacio de tiempo para que los estudiantes intenten resolver por ellos mismos, porque eso es la única forma de aprender a programar.
Correcto.
If you have questions, you can send them in the chat. You can also send them as a direct message. For example, last time, some people sent their solution as direct message to me, so I can check if it's good in the way they did it. There are many options, so feel free to send your way of programming, and we can discuss if it's working. Maybe 10 more minutes to try on your own, and then you look at the solution.
Les daré 10 minutos más para que puedan intentar resolver, luego lo presentaré la solución. Dice.
¿Está rica la comida, Mati? ¿Te encantó la comida? Mati, ¿te encantó la comida?
Por favor, cerrar su micrófono, por favor.
So 2 more minutes, 2 minutos más, and then we will check the solution, and you can compare to what you did yourself.
Está dando 2 minutos para que puedan presentar sus resultados, señores asistentes.
So, if you haven't finished, it's not a problem. You can do the task also later. That's why they are on the material. You can try again on your own and then compare with the solution. Let's have a look. So the first function should take a list of numbers and removes and prints every third element in round robin, so over and over again until the list is empty. So take every third, kick it out, repeat from the start. So let's check the solution. So I call the function remove nums. It's a function definition. It takes a list as input. Be reminded, we start counting at 0, not at 1 in programming. So from the third position, that position is the variable for which element is to be taken out, we subtract 1 and we can just leave the 3. Index is the position where we are, or where we at the moment, and we start at the first one, which is 0. We take the length of the list, and while this length is positive, so meaning the list is not empty yet, we take the index that is always the third. So we calculate modulo the list length just at the position that we want. So in this case, every third position, we subtracted 1. So we end up at the second position, start counting at 0. So 0, 1, 2 is the first index that is to be taken out. Take it out is possible with pop. Pop is a method working on lists, so you can say which element, which index is to be kicked out. This element is to be printed, and then of course we have to update the list length. This was set as a constant variable, taking the list length at the beginning. You don't have to do this, you can just measure the list length again. You get shorter by popping anyway. In this case, it was chosen to update a constant variable every time. So subtract 1 and start over again, go to the next index divisible by the correct position. So the 6th and the 9th and so on until you're at the end of the list, and then you restart again. By this modular operation, modulo list lengths, you directly get the round robin fashion. So we will start all over again until there's nothing more to do. So if we take, for example, this 10, 20, 30, etc., and call the function for this input list. So we stuff this list of integers into our function. Let's run it and see what happens. Then we get the third element, which was 30, the 6th, it was 60, 90. Now these were popped. So we are left with 10, 20, 40 is now the third element, and 80 the 6th, and so on. And this is just the correct sorting of the numbers as we wanted it. So this would be one option for the first task. Then define a function that multiplies two given numbers if they are integers. Otherwise, return an error message. There's also two ways. I show you both, at least two ways, but two ways in principle. Like first one here, using a lambda function, is a one-liner. So I define the function mul as a lambda function. So this is of type function. The lambda keyword defines a function. It takes two variables, two inputs, x and y, and it returns the product if, and now comes the condition, if the type of the two arguments is integer. So we test if type of first argument is an integer, and if it also holds true that the type of the second is an integer, because then we want the product. Otherwise, this is the else case, we print some error message, for example, is a type error. Let's test it. We evaluate the mult function for 3 and 4 and expect, as these are integers, that the result is 12 and is correct. So another way would be to use a function definition with the def keyword. Let's call this function mul2. It also takes two input arguments. You see, not a one-liner anymore. We need indentation now. Again, we do the condition check. We check if type of x is an integer and also type of y is an integer. Both arguments are integers, then we return the product. Else, if this is not true, we print again an error message and then we don't return anything. So you can just return none. None is a keyword. You see, this needs a few more lines. Then the lambda function, but maybe is easier for a start. You don't have to put the condition at the end. You can first check the condition and then return the result. And as you can see here, this is an example for a function that has several returns. This is not a problem. You can either end up in the if case and have a return there, or you end up in the else case and have a return there. So let's try it. I call the mul2 function with two numbers, but in this case, I use a float and as a second argument, not an int. So we expect the error message. If we run it, we see we get a type error. This is the output of this function call. Of course, we can try again if, for example, the other multiplication returns the type error if you add the wrong type, and here we can check if it works for two ints. Let's rerun it and we see now the first one sends us a type error and the second one does a calculation because it was two ints. So this works. No questions so far? Good, then the next two tasks. You were to implement a Python program that adds 3 lists, meaning take the numbers in the list and do mathematical addition. So for example, the lists are 1, 2, 3, 4, 5, 6, 7, 8, 9. You can use map and lambda for this. It's a one-liner again, it's really short this way. So map evaluates a function at a given input. So first we need a function. We can use just some lambda function taking 3 arguments. You always use the lambda keyword and then you come up with all the arguments that it takes. That's what you in the definition put in the brackets, the commas. It takes 3 input arguments. It will be 3 lists and they are supposed to be added. So x plus y plus z. Okay. Let's see if it works. The lambda function is evaluated with map if you give the input where you want it evaluated. If you have 3 arguments, you have to give 3 things as input. Let's check if it works. So what we expect is that you sum up the 3 lists column-wise. And this is exactly what happens here. So 1 plus 2 plus 1 plus 4 plus 7 is 12 and so on. So you see with the lambda function and map, you can do this in one line. And the last task was, please come up with a function that calculates the Fibonacci series up to a given value. And this is a quite fancy way to do it. There are many other ways. So probably you don't have this version, but it's not a problem. So the function Fibo takes a number n, it's supposed to be an integer, can be a float, and then it calculates every element in the Fibonacci series up to n. We start with a tuple. Here we have a tuple definition. We don't need the brackets. We say x and y are supposed to be 0 and 1. So x is assigned to value 0, y is assigned to value 1. Y is the one that we're interested. We need the 0 at the beginning as a start value. So while 0, that's the element in the series where we are at the moment, so the kth element if you want. This is to be printed because we want to start with 1. And then the next two elements, now we shift both, are calculated. So x is overwritten now with the current y. So we basically shifted one step forward in our tuple. And the y is overwritten as well by the next element in the Fibonacci series. So don't be confused by this tuple writing. We assign now x a new value. X is now overwritten and is y. And y is also overwritten and is x plus y. So the next element in the series. And if you tell the function, please do this until you are at a value bigger than 10 and stop, what we get is the Fibonacci series up to 8. So 1 and 1, and then you would come up with 2, 3, 2 plus 3 is 5, 3 plus 5 is 8, and then the next would be bigger than 10, so it's okay there. We stop now. Many ways exist to do this with Fibonacci. So probably yours is different, and you can try to come up with many different ways. So feel free to go on practicing with that task to get used with the function calls and the function definitions. Okay. Now we proceed. Next chapter that we do is the Numpy library or the Numpy module. This is a very important module. You will basically import this every time you start something mathematical in Python. It's the most important library for scientific computing. And it has a very broad functionality. So it can do most of the standard things, and everything else you can combine usually with the functionality that's given in Numpy. It stands for numerical programming in Python. That's why it's called NumPy. It's really fast because actually in the background, this is implemented in C, or in some cases in Fortran. This makes it highly efficient, but you don't have to deal with C. For you, the interface will be strictly in Python code, so you can do everything in Python. And in the backend, as it is interpreted, it will be compiled into C code, but you don't see anything of that, just for you to know. Because maybe you wonder, a few things are a bit specific, and the background is exactly this. Sometimes it's just easier to do it in a certain way because you know that afterwards everything's compiled in C. So we only look at a very tiny part of the module, the most important things. So we start by importing it, of course, otherwise we cannot use it. Here, this line is just for to show you later a few things for plotting, just for the Jupyter Notebook. We will learn about this later. So first we import the module, and I import it to the complete namespace. This is dangerous. I mentioned this last Saturday. I do this here now, and later we will see that it's prone to errors. So be careful with this. By importing the complete module into my namespace, I can omit the Numpy prefix. So what you usually use when importing Numpy is arrays. Arrays is basically our form of vectors and matrices now. It is way better than lists for everything that has to do with mathematics. But it, at the first sight, is very similar. So arrays can be created from lists or from tuples, or also from functions. There's special functions to do this. And also you can read in data. There's functions to read in data and directly stuff the data into an array. First, we learn how to do an array definition from a list. So we use Numpy array function as we are important in the namespace. I do not need this Numpy prefix, as I said. So I can just come up with a list and put it in this array brackets. I say array of this list, and that turns this list 1, 2, 3, 4 into a Numpy array. Let's run it. So we directly see here, this is of type array. This is not a list anymore. And also nested list that we used as a first start to represent the matrix can now be used to deduct a multidimensional array. So here I use a nested list. So a list that contains, in this case, 4 other shorter lists. A list with 4 lists inside, each with 4 elements, to come up with a matrix. Be careful, is a matrix in mathematical sense? In type sense, it's still an array. So let's check what happens. We see now we have basically a matrix representation. Type is array. These are not lists anymore. The lists were just to, to put it into an array. Because when you check the type now, is an array. It's not a list anymore. If you want to know the dimensions, then you ask for it with shape. Shape is a method, so you don't call shape with round brackets. Instead, you put dot shape. So let's ask for the dimension. Remind you, this was our vector v, 1, 2, 3, 4. So a row vector with 4 elements, 4 columns. Actually, this is transposed, so we get 4 rows now as a shape and no columns. Or if there's nothing, then it just means it's 1 basically, but this is omitted. Our matrix had 4 lines, 4 rows, and 4 columns. So we get 4 by 4 as a dimension. Be careful when you migrate from MATLAB. There you ask for the dimensions with size. However, size in Python will give you the total number of elements. That is, in the first case will be 4 elements, as it's 1-dimensional vector. And if you have a 4 by 4 matrix, it has 16 elements. So size would return the 16 elements. So really use shape if you want the dimensions. So you could argue now, why would you come up with these arrays? We had the lists, and if you want the matrix-like object, then just use nested lists. So a list of lists. Why would we use an array? Well, lists are okay as a start, but you can stuff whatever you want into lists. And if you want to have a vector in a mathematical sense, this should not be possible. A vector should contain things of the same type inside and not mixed things. You have a vector for a given field and not for whatever fields you want to put in. Same with the matrix. So the dynamic typing and the mixed typing would be a problem, and Numpy arrays are instead statically typed. So only things of the same type can go in. You need a homogeneous type and is statically typed. So once you created an array, it has a certain type and it would stay this. What happens in the background is you create with C a certain object of certain type, and this will stay. If you want to change the type, then the object is destroyed and another one is implemented. Whenever you want to do any calculations, use arrays, not lists, because it's way faster, as in the background, C and Fortran will act for you. So whenever you want to do more than just look at it and don't use the lists, but use instead the arrays. Import Numpy, come up with an array, use the list as a seed, but then proceed with the array. As it is statically typed and homogeneous, you can ask for the type of elements. Basically, it's like asking for the field behind. So if I use the method dtype, I get as a result, it's ints. The 64 means just that it's a very long int. So the precision, basically. For us, it means only integers are allowed in this matrix. If you want to float, then you need another type. Now, in this case, when I try to put something in that is not of the correct type, hello is a string and not an int, I will receive an error. I cannot put mixed things in a matrix. So if I try to do this, then I get an error. It's invalid literal. It's not an int, won't receive it. Good. Actually, I never said that I want an array of ints. Remember, I just added these. So the type again was dynamically set. Python saw that I was only giving ints, so it assumed that I want an array of ints. If you enter these, but you want them to be floats for later better precision, then you can set a type. So it's possible to declare a type. You don't have to hope that it will guess the correct type that you want. You can set this. Check the help on how to do this. There's many options. You can also set then the precision. There are functions that generate arrays, because sometimes you don't want to put every element by hand by setting it into list. Of course, you can use list comprehension, but very often you just need equidistant points, for example. So then you can use a range, which basically just counts, in that case, from start to stop with given step size. So from 0 to 10, step 1 gives you all the integers from 0 to 10, but the 10 is omitted, mind you. You can also omit the start value. So one argument would be fine too. You don't have to stay within, so you can count from 0 to 1 in 0.1 steps. So you get more elements then. So whenever you want equidistant counting, then feel free to use a range. Also possible, you can linearly or equidistantly discretize a given interval, like from 0 to 10 into 10 points. And then you don't have to think about a step size, just about the number of points you want. You can also let it do this in logarithmic scaling. So instead of linear scaling. So here you say from 0 to 10, I want 10 points. Please, you think for yourself what distance is to be taken. And the same with log space for logarithmic. Just be careful. Normally in a range and everything we've learned so far, this endpoint here is not included. However, in lin space and log space, the 10 is included. This is why you get these odd numbers, because you cannot count 0, 1, 2, 3, because then you, after 10 points, you are at 9 and you won't get the 10. So be careful, endpoints are included. You can also do a two-dimensional grid. We will use this later for plotting. So mgrid or mesh grid is the function here. This will directly broadcast everything in this fashion. So not only from 0 to 4, but already copied so that you have a grid. When you look at one of the parts of the tuple, you receive just the transpose. So also, sometimes you don't want to think of numbers for yourself. You just need some array for testing. Then you can use random numbers. So what kind of numbers depends on the distribution. If you don't use anything specific, You want uniform distribution, you just use rand. Therefore, you have to import random. Then you can use rand. So from Numpy, we import random. And now we get an array of dimensions 5 by 5 filled with random numbers. If you don't specify where they're supposed to be, then they are between 0 and 1 in uniform distribution. You can also use rand n, then you get standard normal distributed numbers. So different distribution. Check the help if you want fancy other distributions. It's possible to enter your own. Very helpful for testing purposes. With rand, you get just some numbers. Then there are a few special matrices. For example, if you want a diagonal matrix, you don't have to set all the zeros by hand. You just tell it it's a diagonal matrix by using diag. So diag 1, 2, 3 sets a diagonal matrix with 1, 2, 3 on the diagonal. You can set an offset to get another diagonal. So this is shifted then. And other typical matrices contain only zeros or only ones. And then sparse matrices can be filled just element-wise in the positions where you need something else beside a zero, for example. Here you have to be careful. I always forget this. You cannot add just the dimension. You have to put the 2 dimensions in brackets. So bracket 3, comma 3, bracket closed, gives you a 3 by 3 matrix with only zeros, or in this case, 2 by 4 with ones. Of course, also the identity matrix is predefined, use the identity. And there, of course, as it is square by definition, you only need 1 dimension. The indexing is, as we have learned in lists, it's just the same. Start counting at 0. There's a zeros row and a zeros column. The vector was one-dimensional along 1 dimension, so you only have to enter 1 index. If you have a matrix like M, then you have to enter 2 dimensions. So the element in position 1, 1, mind you, we start counting at 0 is this one, the 6, which is returned here. And if you only enter 1 number as an index in a matrix, so in a multidimensional array, you get a complete row. So M of 0 is a row. If you want a column, you have to enter the column before column, comma, and then you get, in this case, the zeros column. Of course, if you enter 2 numbers, you get again the explicit element. So by using the column, you can do row-wise or column-wise indexing. This is also possible to reassign a value. Remember, this was M, 1, 2, 3, 4, 5, 6, 7, 8, a few more. And now I say, no, in the first position, I want a 17. So I can reassign. This is not, it's mutable. And slicing works in the same way. You can do just as in lists. You have an array and say, okay, I want every second element, for example, or all the elements starting at 3, then the column just says, please go to the end. It's as easy as this. So with 3 column, you get 3 and onwards. So they're also mutable. You can reassign values. And also, and this is a bit different from Matplotlib, when you want to start counting from the end, is a bit different. There's no end keyword, but what you can do is you can say -4 and a column, and then you get the last 4. So the minus makes it count backwards. -4 column means the last 4 element. And also, yeah, you have a new array with list comprehension. You can, from this big array, this big matrix, you can take out a block. Also with slicing, you can say column 1 to row 1 to 4, a column 1 to 4. This is again 2 to 5 in this case, 2 to 3. So you get these. So you can take out blockwise. And also, of course, you can do bigger strides. Instead of taking every column or every row in a certain range, you can take every second or third or whatever you want by just adding a step. So you have start, stop, step again. And here we take a step of 2. So you get zeros and then every second row and column. So, and by the way, -1 again is the last element. So be careful, it's a bit different than in MATLAB. So now that you have had an introduction to arrays, is again your task to go on. Try yourself, open your console or Spider or whatever you want, and try to play around with Numpy. Of course, you have to import a module, import Numpy. You can import to the namespace or import as a certain name. And then first try to construct a vector of increasing numbers divisible by 3. And then reverse it so that they count backwards. And the next task, create a 10 by 10 matrix, basically an array, 10 by 10. Where everything at the borders is a 1 and inside you have zeros. And the last thing, build a mask using comparison operators to select certain values so that only these are taken as stated here. Read it again for yourself. I will make it a little bigger. And then you have maybe another 10 minutes should be fine. And then we will have a look at the solution. Please, if you have a question, you can send them in the chat. Also as a direct message. And if you forgot something, because this was done quickly, of course, you can always check the help or send me your question. So you have 4 more minutes to try the tasks, and then we check the solution. Okay, then let's check the solution of the first NumPy tasks. The first one was to come up with a vector of increasing numbers, and they shall be divisible by 3. And then you are supposed to reverse the vector. So the increasing numbers are decreasing then. We can do this with a range, for example, because with the list you have to put the input yourself. Just use a range, because then you can say that you want to go in steps of 3. Starting at 0, this makes the numbers directly divisible by 3. So we start at 0, take every third number then, so 0 and then 3 and 6 and 9 and so on. So they are divisible by 3. For example, until 50. A range directly returns an array, we learned this. And if you want to reverse it, you can just use negative step size. So by counting -1 means you are going backwards. So by doing this and reassigning, you can reverse. Because if you only call this without the reassignment, then the original stays as it is. Let's see if this works. Let's run the cell and we see we get 48, 45, 42, etc. until 0. So it works. And mind you, if you don't reassign, if we do this, then the original vector is kept, so counting in increasing order. So you really need to reassign. And in that sense, it is, of course, mutable. So slices are always mutable, also the complete thing, but just reassign, override the old value. Okay, the next task. You are supposed to create a 10 by 10 matrix, in this case array, and the elements on the borders shall be equal to 1, and inside you want zeros. So basically you want a ring or a square of zeros and ones outside. You can do this with slicing. So first we could start with ones. So by calling the matrix or the array boundary and assigning it with only ones of size 10 by 10, we get ones everywhere. And now a block inside is reassigned a new value, 0. And a block inside is just everything from the first row. Remember, this omits the zeros, so it's the real second, until the last by 1. So -1, not the last one, -1. And this we do for rows, first until last by 1. And the same for the columns. And see what happens. So we should have ones and the middle square is taken out and replaced with zeros. If you run the cell, we see we receive the desired 10 by 10 matrix, ones at the borders, the outside, and 0 inside. Okay, the last task was using a mask. Build a mask that uses comparison operators. And the goal was to select values between 5 and 7.5 from a vector that is filled with numbers from 0 to 10. So, good idea to use run, or you fill the vector yourself. And the mask then filters. So, you don't have to take random numbers. You can just use a range, for example, and it's obvious what is filtered out. Random is more fun, but it's okay. So we take values from 0 to 10, and in this case, 0.5 step size, and filter. Therefore, we need to build the mask. We can say we want everything that is greater than 5, but lesser than 7.5 and multiply. So we get both. And then we can do this with fancy slicing or fancy indexing. We now call the mask and set this as index. This is possible, and then we get everything in the mask that holds true in the original array. So let's run the cell and see what happens. First, we get the original numbers. So 0, 0.5, 1.0, etc., until 9.5. And then we filter, and the filter was set to, let's check, greater than 5 and lesser than 7.5. And this is what happens. We have 5.5 and going up to 7.0. So exactly that part that we wanted. So here we are too big, this is too small. So this works. So the fancy indexing that evaluates a comparison operator in the original array to true might be very helpful. You have to think a little more, but very often with this you can get really short indexing, also for complex filtering. So the last way to fill an array is with file IO, meaning you can import data. We do this quickly because at the moment we don't need it urgently, but you should know that it's possible. And when you need it, you just look up the commands again. So here I have a data file that I want to load. When I write an exclamation mark, then this is usually something from Jupyter Notebook. So this is not Python. This is here just to show you what data I load. This just concats the head or prints the head of the file. So apparently the Stockholm file contains many lines. This is just the first one. It has 7 columns giving some values. Actually, it's some temperatures, I think. So that was just for you to see what I want to load. Not the loading yet. This is done now with Python. So the next cell does this for me. Into the array data, I load the data file. And this is done with gen from txt. So this loads data for me. Let's do it. And this was a huge file. So maybe I first want to check how huge was it before I print it somewhere. So we can ask now for the shape, because now we don't know, we loaded it. We didn't set it ourselves. So with shape, you can ask for it. And apparently it's very long. It has 431 lines or rows and 7 columns. So here was only the first column, first lines were printed. Let's have a look at it. This we will learn later how to print, just that you've seen it. So this data it looks like this. This is just 2 columns plotted, the year and the temperature in that year. So huge amounts of data can be loaded into arrays. Here we have different types actually. You have a year, we have temperature, and it's now all in one array because we just require the same data type, not the same unit. So all of these are floats. So it's fine to load into the same array. Of course, this could be interpreted in general as an int, but as the full file is loaded and Python sees, there's also floating point numbers, it will set the type of this array to float. Of course, you can check by what the type is with dtype. Another way of inserting data is by using random. We've seen this before. And as we are doing file IO, I show you the O as well. So we can also not only load data, of course, you can also save data. So for example, maybe I want to keep this fancy random numbers. Maybe I use them as some start value and want to redo the task with the same start value. And I want to save it. And there's also an option with save txt. Then you name where you want to save it. You can, for example, use comma separated files or something else, data file. And then of course you have to specify what to save in that file. So file name and what to save. In that case, I want to save M. By using this again, this is not Python code. This is again only for Jupyter Notebook. I can now print to into the console here. So apparently I saved this. Also, you can see that I saved it with quite some precision. Here, the precision is hidden because for the print skips a few of the numbers. Okay, if you want less precision, you can set it. You can specify the format. So here I cut off after 5 digits behind the comma. So now the fun part comes, because what we want to do with Numpy is we want to do mathematics, of course. And as we've learned, most of the things, they exist already. For example, the math module. But if you import Numpy anyway, you can get everything you need from NumPy. So everything that we've seen in math is already there in Numpy as well. For example, the sine, exponential function, power function, important constants, they are all there. You can just call them. You can do typical rounding. For example, you have a floor function. You can also, mind you, this was a Numpy function, floor, and I inserted an array, but you can also insert a list. So ceiling is possible. So going to the next highest integer. Here, for example, was lists as input. But now here, that was the warning I gave you at the beginning. Be careful when you import to the current namespace, because in this case, this happened to myself. I was lazy, I imported to the namespace. So what happened is I can use round directly without saying NP or NumPy round. But round already exists in the original Python without any module loaded. So when you import to the namespace, this is not overwritten. So this is the original round from Python. It's not the NumPy round. And this doesn't work for lists. The original round can only process a single number, not a list. So I receive an error because this is now not NumPy round, it's Python round. If you want explicitly the NumPy round, then you have to state it. So now I import NumPy as NP. Now I need the prefix. And then it works. Now this is NumPy round explicitly, and NumPy round can deal with lists as well, or arrays, or what you want. And also you can set parameters. You can say the precision shall be 1 decimal, for example. It's not possible with the original round. So be careful. Usually you never import into namespace. You should always do like this actually. But I was lazy for the notebook too. Another nice thing that you can do is you can calculate the roots of polynomials. You just have to give the coefficients. For example, this polynomial coefficients 1 to 1 has the following roots. You can calculate, of course, yourself. -1 is the only possible solution. This was easy, but of course, sometimes it's a more complex polynomial and maybe you don't have Wolfram alpha at hand, then you can use roots. So typical mathematical functions are available and also typical procedures, such as calculating the roots. But the most important part is the linear algebra that you can do with NumPy. I mean, apparently the shape of the objects tells itself. This is like a matrix or like a vector. Arrays, they already look like a matrix or a vector. So the most important part is to do or to perform matrix vector operations. For example, matrix by matrix multiplication and so on. So this is basically what you usually do when you import NumPy. We deal with matrices and vectors, and everything you want to do that you know from mathematics is available already. So you have scalar operations. We start with the element-wise operations. So scalar operations, like a vector ranging from 0 to 5, you can multiply it by 2 every element. So element-wise, this is done. So you have a normal scalar multiplication with a normal multiplication sign. This is possible also with multidimensional arrays. So here we have this array, a 5 by 5. And also we can multiply by 2 or we can add 2 and every element. So this is element-wise. Of course, there was only a scalar given, but might happen that you want to do element-wise operation when 2 matrices are given. Here you have to be careful because MATLAB is normally not element-wise. You have to specify explicitly if you want to do element-wise. If you don't, it's a matrix multiplication. Not in Python. So if you have two multidimensional, in this case, square arrays, we have an element-wise multiplication, not a matrix multiplication. If you do this with different shape, but compatible, you get it for each row in that case. So we have here a matrix and a vector. Check the dimensions, 5 by 5 matrix or array, 5 by 1 vector. You can multiply and then it's done row wise, because now element wise it's not possible like for every element, as here we have lesser elements. But you can do row wise. Now, usually you don't want to do element wise things, at least if you enter two matrices. Instead, you want matrix multiplication. So you can do this with dot. Dot is a way to do matrix or matrix vector multiplication. So dot, and then you enter two arguments. In this case, for convenience, I just took A twice. Of course, you can insert any other array of a dimension that would fit into this operation. If the dimension is not okay, then you will get an error. So dot with A and with matrix and vector is possible in this case because the dimensions correspond in a good way. And also vector. In this case, we have actually directly a transpose, so we get the scalar product. What you also can do is make it a matrix in a type sense. So I usually use the term matrix because when we come up with an array such as here in A, what we mean by it is a matrix in a mathematical sense, of course, because usually you want to deal with matrices. It's an array in type sense, as you can see here. So the type of it is an array. There's actually a real matrix type. You can use the function matrix to make it of type matrix. Let's run it. So now we have matrix A and matrix V. This makes it a column. Now we differentiate. This is the transpose. So we have now a column vector. If things are of type matrix, then it matters if it's a row or a column. And you have to be careful because now when things are of type matrix, so not only matrix in our head because we think of a matrix representation, then all the operations are done for matrices and not element-wise. So now the normal product with the star for matrix of type matrix is not element-wise. Now is the normal matrix multiplication. So this is a common source of errors. But normally it's actually not necessary to define matrix. We typically stay with type of array. And then you have to know that the normal way is then element-wise. Many other functions exist. You can calculate basically everything that you want to calculate for a matrix or a vector. You can ask for the mean, so the average value, mean value. You can calculate a cumulated sum. So there is a lot of functionality in the background implemented. There's already a loop going one step further in the vector and taking the sum that was calculated before and adding the next. So this is a cumulated sum. You can calculate typical linear algebra stuff like the trace. So the sum of the diagonal elements and everything else, you know, from linear algebra. So the determinant, for example. So this you can do with matrix, but you can also do with array. So here I have an array. I can calculate the determinant. In this case, it is non-zero, so I can also calculate the inverse of this matrix with inf. But be careful for this typical linear algebra operations. You need to put a prefix linalg for linear algebra. You cannot use directly det or inf. You have to call it linalg inf, or maybe even numpy linalg inf. Of course, also eigenvalues can be calculated, and also the eigenvectors that correspond to it. And if you want to do numerics, very often you need to know the condition number of a matrix. Also, this is already there with cont. So basically everything you want to do. And what you also want to do very often is you want to solve a system of linear equations. In this you can do with linalg solve. So also very important. Here, as a reminder, I added the NP. I imported twice now. So you can omit the NP or you can set it. And if you use linalg solve, you can solve systems of linear equations. So I have here a matrix and the right-hand side. I want to solve the corresponding system. So I want to know, actually, I didn't write it down, but basically what I want to know is the solution of ax equals b. And this x I get by using linalg solve. I mean, this is a short system with two equations only. But more complex system you don't want to calculate by hand, and then you use this. Many more functionalities there. You can do singular value decomposition, QR decomposition. As I said, everything you want to do in linear algebra. Okay, now it's again your task. You can try yourself. There's another 3 tasks for you. First, you construct a matrix. Just to, it doesn't have to be of matrix type, array or matrix, just to get a feeling for these multidimensional arrays. It shall have 4 rows, 5 columns, and every entry is a 6. Then you write a program with a given vector b that is added to each row of a given matrix A. And as a last thing, you can compare 2 commands, use the help or try them out with examples. The star product, the normal multiplication, compared to Numpy multiply. And you should do this once for arrays and another time for matrices and see if there is a difference. So this is the last NumPy task, and when they are done, then we will proceed with the next topic, but we will have a short break before. So now you can work on the tasks. We will just combine it with the break. So let's say it's maybe 10 minutes for the task, and then we have a 10-minute break. So in 20 minutes and 20 minutos, we will proceed with the solution and go to the next step. So 20 minutes from now. I just write it down here. So this should be, here it's 10 p.m. So probably it's 3 p.m. now in Peru, right? And let's meet 20 minutes later so that you have 20 minutes for the task and the break. And if you have questions, send them to the chat.
Señores participantes, como está indicando nuestra ponente, en 10 minutos tienen para hacer la tarea, 10 minutos de break, estaríamos retornando 3:20 p.m. Thanks, Vanessa.
Welcome. And if there's a question, just post it in the chat or send it as direct message.
Lídolo un poquito.
So then let's start where we stopped. I received a few solutions. Thank you for that. Muchas gracias por las soluciones. So really nice ideas, very short and compact, and all were working very nicely. So very good. Let's see one possible solution here. First, there was an easy one just to get to deal with the matrices arrays. 4 rows, 4 columns. Every entry set to 6. So this we can do. For example, by setting only ones in the given dimensions. 3, I think it was 3. Was it 3 or 4? Hope I did it correct. Oh, 4 rows and 5 columns. So that's not correct. 4 rows and 5 columns, and then we multiply scalar multiplication with 6. So this is an array. If you really want a matrix, you can just retype it to a matrix, for example. So let's run it. So here we have an array with containing only 6s, and when you retype it, the matrix, then it's a real matrix. But both versions are fine. The array is fine. So the next task, a program that adds a vector b to each row of a matrix A. Matrix is now again mathematical sense. You can stick to arrays. Okay, take any array. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And a vector 1, 1, 0. This is, by the way, an option we haven't learned about, to predefine an empty array of the same dimensions as something else. You can use empty line. It's, of course, you don't have to know this. We have learned it. It's just here to show you another option. Also, you could use zeros of the size or of the shape of the dimensions of M given. It's also an option. So these are 2 options that would lead to the same result. By the way, you don't have to predefine, but usually it helps. I will tell you why. So if we use now a for loop to fill the elements. And we want to add and reassign new values. So we do this with a loop, for example. Broadcasting is another way. But you could do it with a loop. And if you predefine the result, then it's already there and you can really access all the points. If it doesn't exist, this would work actually, but you have to think what happens in the background. In the background, you would destroy the object every time it changes its size and make a new object and copy what was there. And this is a lot of stupid work. So better predefine an empty array of the correct size. This would be done here by one of these 2 lines. And then you fill the result with the correct values. For example, you do a for loop, 4 steps, and add in the correct way for the 4 rows that we have. Be careful. Here we set a magic number 4 because I know that this was 4 rows. It would be better to use M shape of 1, so the first dimension. So because then it would be more general and it would work for another M of other dimensions. Let's check if it does what it's supposed to do. So these are the original ones, the vector and the matrix, and then this vector is added to each line. So 1, 1, 0 plus 1, 2, 3 is then 2, 3, 3, and so on. So it works. Just one way. This is, for example, a quite long way. There are shorter options. But maybe it's the first thing you come up with. Let's check if there is a question in the chat, but it doesn't seem to be. Okay, the last task. Compare the commands A multiplied with B using this star command, and also use NP multiply AB. And then try this out if it is a difference for arrays and for matrices. So what you do is you just use it and test it with adequate test cases. This is done here. We predefine an array. And then we check, is it a difference if I do A times A with the star product compared to multiply A with A? Of course, you can use AB, but just for a quick test, you can reuse the one array. If this does the same, if both things do the same, then everything should equal to true. And then I test the same with matrix. Here you can guess it's not equal anymore because I print m times m separately from multiply m with m. And actually we get something else. Let's run it and see. So true, 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 true. In the first case, this is A times A equals multiply AA for arrays. So we learned this is an element-wise operation. So apparently multiply is also element-wise. It does the exact same thing if you enter an array. But now I redefined and I made M a matrix with the same entries as the array. So this can go out actually. And now this normal multiplication is matrix multiplication that we already learned. Here it works with m and m because m is square. Be careful with the dimensions. And now if I use multiply, I go back to the element-wise multiplication. So this is basically overwritten by turning A into a real matrix of type matrix. But multiply stays element-wise. Multiply is always element-wise. So if you handle matrices of matrix type, then if you want to perform element-wise operation, you can, for example, go back to multiply. So these were our last tasks with Numpy. I already uploaded the material to the folder. So you have it at the ready. And we will now proceed with plotting. I tried to go over this quickly so that we can then go to the pandemic modeling in Python. It's a bit more interesting than just learning the basic commands. And at the end, by the way, Stefan Frey will come and introduce the project. We have a follow-up project that you can work on yourself if you want. And this might be interesting, for example, for students who tend to go abroad and maybe go into numerics or so. Maybe have a cooperation with Germany. So after the plotting and the modeling, Stefan will introduce you the project. Okay, let's go to plotting. Matplotlib is now the module or the library you want to look at after NumPy. Is this very important because sooner or later you want to see what you calculated, or maybe you want to make figures for your paper or your master's thesis, and then Matplotlib is what you need. Again, this is just for Jupyter Notebook. This is not Python code. It's running to show you the plots right away in the Jupyter Notebook. Just check the chat. No NumPy questions. Then we start with the plotting. Okay, so it's a really nice library. You can really do everything you want when you need for scientific papers. You can do 2D and 3D plotting. You can use LaTeX code. So the labels already look nice and you can finish the complete figure in Python. You don't need to polish it up later so that you can put it in your paper. You can use all the typical formats, export it in whatever way you want. And this is important, all aspects of the figure can be controlled programmatically. So you can change it later. So if you send a paper to some editor and they don't like it, or they say, we want another font size, you don't have to start all over. You can just use one short command and change things. And this is great about it. So also you can keep common scripts that you can reuse for typical plotting, setting the font size and the axes and labels in the same way for all your figures. So you save this once and then just change the plot itself, so the function at the plot. Okay, so the module we look at is Matplotlib. We have to import it. Again, I do it to the current namespace. Usually it's better to import Matplotlib pyplot as PLT for plot, so that you don't get into trouble with namespace overlap, as we have seen before with round. So let's run this cell, and also let's import NumPy again, we will need it. And if you migrate from MATLAB, you will probably learn it very easy. It's quite similar. So there's MATLAB-like application programming interface. So basically, you can reuse the commands you know from MATLAB. The simplest thing would be we want to plot a two-dimensional curve, for example. This function, the x values are 10 points between 0 and 5, and we want linearly spaced, equidistantly spaced, and we want the squares of these. So the function would be a square function. So calculate the values first, of course, the x values, the y values, and now assign them to the different x's of the plot. By calling figure, we set a new figure. You can omit this, by the way, but then everything goes in the current figure. And we basically say plot. First the x dimension, then the y dimension, so the horizontal and then the vertical dimension. And here you can set, but you don't have to, a color. So this is a string. You see this because you have the quotes. And there are shortcuts. So R means red, and for example, B means blue, and so on. You can look these up, you don't have to know, but they are basically self-explanatory. And also we set labels to the x's and the title. Let's check what happens. So exactly what you say, we want to plot x versus y. So these 10 values on the x-axis and the squares on the y-axis. So leading to the half of a parabola. And we label the x's with x and y, and we gave it a title as a square function. That's it. You can actually, in most cases, you can omit the show. So we brought in our function here. It's red as we specified. This was like the easiest way to quickly plot something, but of course you want to do more things. For example, you maybe want two plots next to each other to compare. And then you can use subplot. You have to name how many subplots and in which arrangement. So here we have subplot 1, 2. This is the dimensions, and 1 is the first one. So last entry counts up the subplots. So first give the dimensions. And then this is procedural, by the way. the object-oriented part comes later. So we have first subplot and then what's going in there. So strictly procedural, call the first subplot, plot what you want, call the next one and plot what you want in there. So it's not really assigned. It works by doing it step by step in this order. Meaning if you want to change something later, it's hard to call it back. It's possible, but it's easier if you set handles. We'll see this. But the advantage of this MATLAB-like plotting is it's super easy. So let's see what happens when I do this. Let's run the cell. And here we see, okay, apparently we have two subplots next to each other. So apparently these are the dimensions, again, the typical order, 1 row, 2 columns. And then the first of the two plots is the left one with the red function. And we just plotted the y versus x in the right plot, which is the second of the two in a 1 by 2, basically row vector. So easy if you want several panels to compare something. And as you can see already, the plotting differs. So you can do everything in one line, just stating in the same string the options for the line, same color, and here you will make it dashed. The green line, G is for green, gives us another color. And here we want the 10 points. Remember, we did this for 10 points. This was discretized. And then the discrete points were connected by a line. We want the markers set to little stars, and then we want to connect the line. Not with dashes, but just one dash makes it a continuous line, and 2 dashes makes a dash. So you can now actually plot it in the same thing if you want, because they are distinguishable by color and marker and everything. As I said, it's now a bit harder to later change things because it's procedural, so you have to go to the right position. Better, you use object-oriented plotting, meaning that you set handles to things, and then everything exists as an object. So the axis exists as an object that you can call later and tell them to change something. Same for the curve itself. So everything becomes an object now, as we learned with the class example. So you have principal classes like x's. X's behave in a certain way. And then you have explicit instances like x's of the left plot and x's of the right plot. And you can set a handle and call them separately whenever you want. Setting a handle basically means giving them a name that you can address. So, as I said, this is again object-oriented. So here we set the first handle. The figure itself, the whole thing, we name now figure, and we can talk to it later. This is of type figure. Also, we set a handle or a name for the axis. So later we can call them again. Now, we can use the axes and tell them, please plot now on to these axes, plot x and y in red. And also you can set the label again and the title. Let's check. Looks a bit longer than what we've seen before, but is better if you want to change things later. So we have full control and can change things later on. Okay. Let's do this a bit more complicated. For example, here we have a lot of unused space in the top left corner. So maybe you want to set another plot there. And this is possible by now coming up with new axis. We have a main figure. We call the axis of the main figure axis 1. So we talk to figure 1. Whenever we call axis 1 is our handle. Here we set the axis dimension. Axis 2 shall be the name of the axis from the second plot. and it has different dimensions because it will be the inset. It has to be smaller and in another position. So when we run it, we receive the main figure here, the red plot. That's the big one, the one that we talk to whenever we call x is 1, and whenever we call x is 2, we talk to the inset. In here we say x is 2 receives a plot in green, and it receives y versus x, not like here x versus y, and it of course has then different labels and has another title. Many ways exist to do stack plots or plots next to each other. If the same thing shall happen for several panels, as is often the case, you can just use a for loop and treat all the x's in the same way. So many ways to do this. You can set whatever you like, the size, the aspect ratio, the number of pixels inside, of course, way more design things that we look at. So for example, here I decided to have it very broad because I set the figure size in a different way. Now it's a width of 12 and a height of 3. So if you don't set it, it's set automatically in a way that Python thinks it looks nice or fits the space well. But you can reset it. When you save, you can also set the amount of pixels and the type. Saving is like exporting, so you can decide into what file type you want to export. So with a save fig, you would export it and name, of course, what file it's supposed to end up. And also you can set optionally, can be omitted, the DPI, so the amount of pixels, or a lot of other things. Then you can set, as we have seen before, set the title, for example. You can set labels by set X label, Y label. You can set a legend. If you plotted several curves, have you seen this here? Oh, no. So far not, but you can plot several curves within one panel. Then you can just in the legend name the curves separately, curve 1, 2, 3, but this is careful, be careful, this is dangerous because then it is done in the order that it was plotted and maybe you change things later and then it's wrong. So here it relies on some temporal order that was kept. Better you name the curves, give them a name so you can talk to the curve. And this is done by labeling, not labeling the axis, but labeling the curve. This is done here. So here I want to plot in the same plot. You see here, I talk to the same axis. They are named X. I want to plot X squared and X cubed. And I can set a label. I can name the first curve square and the second cube, for example, so I can distinguish later. And if I do this, I wonder why it's not plotting anymore. Probably I didn't run everything that I need. When I do this, then I just need to call legend and the labels are set automatically. And if I, for example, all of a sudden outcomment this, then it's not a problem. The legend will be the correct way. You can also set the location of the legend. So if you don't set it, it is set to a space where it's free. But if you want it in another position, maybe there's two options, then you can set the location. So here everything is put together. You have a new figure, new subplots, and I want to plot two things, and I labeled them directly. Here again, my square and my cube. I set label, and then later I only call legend. And then it is directly labeled in the way I defined it when I plotted. And now if I take one out, then it's again automatically the same legend. When I take it back in, it's already back there. And if you here name the labels, then you have to change into positions. So better you do everything you can directly where you need it. If I change location, I can send this to another position, but here is no good. So better let's put it back to the upper left corner. And of course, you can also format every label and whatever you have. All this is possible. LaTeX is possible, as you can see here. Sometimes you need to explicitly allow this. So if it doesn't work, Google it. And as you can see, now I have alpha squared here, just in typical TeX code. Also, the font size of the labels is way bigger. It was reset to 23. All of these things you can do. You don't have to know by heart. No one knows this by heart. The plotting you just look up when you need it, or have your typical plot library at the ready. You can set different colors. We have seen this before. You can, for example, choose also hex code or RGB hex code or whatever, not only these pre-named typical colors. You can use different styles for the line markers. Again, you don't need to know this by heart. This is just to show you what is possible. So all these style types are possible. You set them with the keywords. For example, color, line width can be shortcutted to LW, line style, the dashes is LS, marker and marker size is self-explanatory. So you have many options. Just check it out whenever you need it. For example, now, because now you can do the first task. Write a Numpy program to compute X and Y coordinates to plot a sine curve, and then also plot it using Matplotlib and label the axis. And in the second task, you do this for sine and cosine curve and place them together in one figure and distinguish them, for example, by color or marker or line style. And add a legend. So you can now again work for yourself. I think 10 minutes should be fine. And then we proceed with more plotting and 3D plots. As we are short of time, maybe we only say 7 minutes, but this should be fine then. maybe 2 more minutes and we check the solution. Okay, then let's have a look. So first, plot a sine curve, label the axis. Let's see how we can do this. Of course, first we have to calculate the points for plotting. This can be done with NumPy. Use, for example, a range from 0 up to 3 pi with depths of 0.2, for example. Calculate sine of these points and then plot x versus y. You see you don't have to set a color. You can just say plot, label the axes, both of them, and then show the plot. Let's run it. This is the first plot. As we specified, from 0 to 3 pi, 1.5 periods of sine. Sorry. And if you don't set the color, it's automatically set to blue. The labels are set, also some ticks are set. And for the next task, you were supposed to also plot cosine. So what we have to do now is calculate the values for cosine as well. We can reuse the x values or the same x-axis anyway. But we have to define that we want subplots, and we set a figure size of 8 and 4. You don't have to do this, you can. And what you then do, now I named this, I gave it a handle, I called it my x. So I can call it twice and plot twice a line into these x's. So first I call the axis my x and plot x versus y in blue. And then I do this again and plot x versus z. X can stay the same. I mean, z was calculated at the same values anyway. And this time I set color red. Also, I changed line width and I changed label and marker. Let's see when we run it, what happens. I also added a legend. Now here we received the full plot. It has a different size because I specified it to be 8 by 4. And the 2 lines appear, blue and red. Different markers and the labels of the legend are set automatically. This time I did not label x and y axis. So this is not taken from here because it's 3 different axes. Okay, so you see this is done in few lines only, a very simple plot. It's really easy. And only if you want to do fancy design, you require like a bit more, like line widths and marker and so on, but most cases you don't need that. So you have, of course, a lot of control. You can set the range from where to where you want to plot. Even if in this case, for example, we calculated from 0 until 3 pi, or maybe you want to plot only from 0 to 2 pi or from 2 pi to 3 pi or whatever you want. So this is independent of the range where you calculated. You can set it broader or smaller, but of course it won't plot anything if you didn't calculate it there. So, but you can only show a part of it instead of the full aspect ratio. So for example, here, I set default axis ranges in the first case, and in the second case, I call two axes here. The second case, I set it custom. Let's see what happens. So here we get the full range, basically where we calculated it. The set's a little space, so you see that you really stopped calculating here and it started only from here. And on the right side, we basically have a zoomed in picture as the custom axis range was set smaller. And then we basically zoom in automatically. You have also control of the axis. You can do logarithmic scaling. This is very often important to have this at hand. So here, for example, we have the normal scale on the left side. What is plotted is a power function to the power of 2 and also an exponential, which rises or increases pretty quickly as it's exponential. So if you want to compare these, it's better to go to logarithmic scale. Here in the right panel, this is done. You see left axis, this is the axis there in list or an array. So in first position is the left side and right position. At position 1 is the right panel. Left side is normal scale, right side we plot the same functions, but we set the y scale to log. If you don't set this, is linear is the default. And if you set it to log, you get logarithmic scale. You can turn on an axis grid. If you want, you can set parameters, you can set it dashed and whatever, it's not so important now, just that you know that this is possible. You can also do, you don't have to care about the code now. I just show you options that you can look up when you need it. But you don't have to know this now. Just know that it's possible. But you also can do, can set the left axis different from the right. So you have basically two twin axes in the vertical direction, for example. This comes in handy if, for example, here you want to plot two functions that don't have anything to do with each other, a volume and an area for whatever, depending on whatever. And then you can assign two axes and have them in the corresponding color to the curve. Many other options exist. I will quickly show you a few examples because we have to proceed. So what you can do is, for example, you can look at scatter plots like here with scatter. With step, you can do step functions. With bar, you can do bar charts, and you can also fill the curves, fill the space between two curves with fill between. Just that you've seen it, many options possible. Also, you can do polar plots, histograms, things like that are possible. Histograms can be done with hist. As I said, you will find everything when you need it by just checking the help or Googling. And then you just check when you need it, what parameters you have to set. So then there's options to do to plot three-dimensional data, the first option is to stick to, for example, if you want to print it, to keep it two-dimensional, but color code the third dimension. So for example, here I define some function I want to plot. It takes 2 input arguments and plots a third dimension. And to do this, I now use p-color. P-color is one option to now color map the third dimension flatly into 2 dimensions. And yeah, instead of doing 3D, we color code, set a color bar next to each other. And another option instead of p-color would be image show or im show. There are many options. For example, you can set the color map correctly and so on. You can set the shading, the type of interpolation that is done, things like that. I won't go into detail. You just look it up when you need it or check the notebook for details. You can also do counter lines. This might be helpful when you, for example, do optimization and you implement some gradient method. Then you might be interested in counter lines as well. You do this with counter. Also can color code done. And of course, if you have 3-dimensional data, you can also do 3-dimensional plots, like real 3-dimensional, not only color code one. There we need to import a bit more for the 3D. I really do this quickly, just that you've seen it, and we proceed to the sphere modeling. The easiest way is a surface plot. You call this with plot surface. This is the command. And what is important is that you have to enter, of course, 3 things, because you have x, y dimension and the z that is to plot versus x and y. But the x, y, and z need to be of a specific type. They need to be of mesh grid type. I skipped this real quick when I did this here. So the 2 dimensions are not just vectors, x vector and y vector. Instead, you have to define a grid because you plot it on a grid. So you cannot deal with just the axis below and the y-axis. You need every point on the grid, and this is done by adding the 2 linearly spaced vectors into the mesh grid. We had this before. This just basically fulfills that you have every point in the grid, and this has to go into the surface function. As the same for the p-color. Let's quickly look at the result. When we have time at the end, we can go back to this, but I think it's more important that we do the sphere modeling. So things like this you also can do. Many others, wires, for example, like this, instead of colors. Or again, counter plots with a projection. So feel free to experiment with this. We also have a task here, but I would suggest that we skip this now. And you can do this on your own if you want, or maybe we have time in the end to have a closer look at the modeling or the plotting. But at least you know now that it's possible to have fancy 3D plots. Okay, questions so far? No. Okay, then now we will go to a more interesting task. We've learned a lot of commands now, and let's now look at the typical problem that you might encounter when you're a mathematician and do numerical mathematics. Then you don't do only like tiny short programs, but instead you maybe have to come up with a real model and implement it completely, and also come up with a numerical strategy to get a solution for something. And then you want maybe to print it. So you want to combine many steps now. And we will do this with the model for the spread of a pandemic, because nowadays it's a common topic. I think I have to switch now the share. So I start sharing another screen. Probably I can just share the complete desktop. So you should be able to see my screen again. So what we want to have as a task now, we want to model the temporal behavior of a pandemic. And we want to calculate this numerically and use Python for it. First, we need to go a little bit into theory. Probably you know the model. Many talks about this type of modeling. I will quickly go into the numerics as well, but real quick. Don't worry if you don't understand anything. The most important part is how to put it later into Python. Okay, let's look at the SIR model. If you have, for example, a country like Germany or Peru, where a pandemic spreads, or first an epidemic disease, then you can, first of all, within your system that you look at, for example, Germany or Peru, you can divide every individual in a population into one of three compartments. So if there's a disease that spreads, you can either be a susceptible host, meaning that you are not sick yet, but you can get the disease, or you already have it, and at the moment you are infectious, or you had it and are a recovered individual. So you have three compartments you can be in, either susceptible, like potential host, or actual current host, infectious, or recovered. That's why the model is called SIR, S for susceptible, I for infectious, R for recovered. Let's illustrate this. We have the three compartments. And the susceptibles, of course, can get infected and then become infectious, which then these people can again recover and they end up in group 3. This is the most important way we look at it. Of course, it can happen that people drop out of the system. Removal means they die or just migrate out and move wherever. For example, we only look at Germany and somebody leaves the country. Of course, new people can come in as well. And what also can happen, we assume that when they come from outside, let's assume they are susceptible, not infected. But also could happen that you go back from group R, from recovered to susceptible, because maybe after a while you're not immune anymore. So a full model would contain at least these transfers. But for the start, we will look at the simpler version. I said already that later Stefan will introduce the project. And if the project will deal with this sort of modeling, the SIR model, and in the project, you are invited to do more complicated things. For example, model it completely, or also enter vaccination, something like this. We now, for the start, look at the simple version. We say no removal and no new people come in. So nobody goes out, nobody goes in, and nobody dies. And also we say once you are recovered, you're recovered, that's it, you're immune then. So way easier, we only keep the middle part. Meaning we have only this simple SIR model, you're susceptible, become infected, and from here you recover. Furthermore, we assume that the total number of people in this model is constant. So the total number of people is the sum of the susceptibles, infected, and the recovered. So now we look at the rates. How can you go from S to I and from I to R? So we can derive a set of ODEs to model the behavior. By looking at rates or at the transfers from one to the other compartment, we can come up with equations for the time derivation. Yeah, because the change of one of the two numbers, of the three numbers over time is just what goes in and what goes in and what goes out. So from S to I, it's easy for S. Only things go out. You're susceptible. You can get infected. I receives new people that get infected and has a loss of people who recover. So let's look first at this passage from S to I. So this passage basically describes how people become from susceptible to infectious. This depends, of course, on the number of contacts that people have and also on the disease. And this is modeled in some parameter beta is greater than 0, otherwise nothing happens. So it models how people become infected. Of course, it depends on parameters we don't know. This is also, all of this goes into beta. But of course, the number of contacts is only relevant or only leads to an infection if you meet somebody that is susceptible. So we have a factor of beta and the part of people who is susceptible in the total amount of people. So a single person that is infectious will affect this amount of people per unit of time. And the beta we need to know from somewhere. Beta, of course, might be time dependent. For example, first it has some value and then the government takes issues or measurements and decides, okay, everyone has to stay at home, we go into lockdown, and then beta is different than from before. For now, we stick with the time constant beta. So this rate describes how many people are infected over time. So is a negative rate for the susceptibles. You have a loss of susceptibles when they get infected. And just with opposite sign, you add, of course, infected people to I with the same rate, because this is just a passage. So the time derivative of I is given by this as an input. And of course, here you have people that leave I and go to R. This passage is still missing. We have to add this. So let's look at the passage from I to R. Of course, once you get sick, you can recover. Here, no one dies. We said this. So with some parameter gamma between 0 and 1, you recover over time. It basically describes how long you are infectious. So this rate of people going from I to R, from infectious to recovered, is just the reciprocal of the average duration of being infectious. This is all stuffed into gamma. So the time derivative of R is positive with gamma and I. And of course, this amount of people from going from I to R has to be subtracted from I. So with negative sign, this rate appears in the time derivative of I, the infected. So this is the second passage that was missing. So now we have a set of, in total, 3 ODEs. So here you can see all 3 of them with the 3 rates. And what we do now is actually we get rid of 1 because we said the total is constant. So if we know 2 of them, you know the third one. So we end up only with 2 ODEs. So a system of ODEs can now be solved numerically. Before that, we will do a few things. For example, we normalize it. So the small s and the small I are the normalized susceptibles and infectious, depending on the time. We have 2 ODEs left. We have the first derivative in time, and we have a right-hand side that we just basically modeled. To solve this or to get a unique solution for S and I, we need to set some initial values. Of course, now it's normalized. So in total, S and I have to sum up to 1 because that's the amount of people that we have now. Or that's the 100% if you wish. So with this, you can go on and do some numeric. This corresponds to a general system of ODEs. We have initial values, so we can go and discretize. I don't know if everyone has had already a numerics class, so we quickly repeat what we do now. It's a very easy method to start with. It's a forward Euler. It basically means that we discretize and do a very vague approximation of the derivative. So what we want to find is a solution for a set of ODEs, given initial values. So what you do first is we discretize the time interval. We say, okay, we have n+1 points in time now in a certain time interval. So time is now discretized. And for these time points, we want to find the solution. The easiest thing is to do equidistant time steps with step size h. Then, when you only look at the solution at these discretized points, of course, the solution is also discretized. The kth point in time leads to a kth function value. With this discretization, we can go on. What we know all the time is the value of the derivative. And this can be replaced now by a difference quotient. That's the whole idea. So for example, if the blue curve is the exact solution that we don't know yet, that's what we want to find, then we can start with the initial value. The x0 is given, this initial value, and what we do know is the value of the derivative. So we can go along the tangent because we know where the tangent lives. We know its slope and we know 1 point on it. So what we do is we go one step in time along the tangent at this point and end up at x1. Again, we now know the derivatives, so we again calculate the slope of the tangent and do another step and so on. This is done here. Of course, as you can see, this is not the correct solution. It's an approximation, but at least you can go stepwise with tangent slope, because that you know, and of course you don't know the exact function value. So what you do basically is you approximate now in zeroth order the derivative by a difference quotient. If you want to know how the error is and how this develops, of course you can do higher order things. You can choose other method. You can do Taylor expansion to at least know the error. But for now, we take just the simplest difference quotient we can think of. So the derivative at the step before is given by the distance in the function evaluated at 2 points and the step size divided by the step size in time. So since we know the right-hand side and we now have an easy new left-hand side, we can now resolve this to the current xk. And this is now given recursively. So the new point that we approximate is given by the one we were before and the step along the tangent. So the slope that is calculated by the right-hand side of the ODEs. So doing this step and then this and then this, as I showed you. So these are the set of equations that we have to implement now with this forward Euler strategy. And this is the algorithm we use for it. It's a general Euler method, and it takes, as I said, it takes an initial value. We need to know the right-hand side, and we need a certain grid size and some final time t, because we won't do this forever. What we then do is we start, as I said, at the first point in time. There we know the value, its initial value, and from there on we calculate the next point in time by taking the one before, the value of the function there, or the approximation, and then doing one step in time and evaluating the right-hand side to get the slope of the tangent. Then update, go one step ahead in time, and so on. So this is the general Euler, and we do this now for the set of ODEs that we just derived, which was the S and the I. So here's the same thing. We just now the set of ODEs that was stuffed into X is now two equations separated for S and for I, and the two different right-hand sides for it. And for these, we know already what to put. And now we want to go and use Python for it. So I probably, no, you can see, I think, the complete screen, I think, so I can directly. There's a question in the chat. Explicar cómo obtiene el parámetro beta. Let's assume for now that we just were given the parameter. The incidence rate has to go into beta, and basically information that you need to require from other scientists, because the disease plays a role, the number of contacts, all this ends up in beta. For us, it doesn't matter. Let's assume we were just given the beta, and for now is only a time constant. So let's go and model this. We start by implementing a general forward Euler method that we will use later, so that we can, call it up when we need it. So you can try, by the way, now alongside while I do this here, and see with what you can come up. So what we for sure need is the Euler method. So for this, we first import Numpy as NP, and as we for now only want to, maybe I may make this bigger that you can read it. As for now, we only write a method. We will now save this in a special file, for example, a file named functions or so, where all the functions go in. And later we write a main program where we call up these functions when we need them. So we for sure need to import Numpy, and now we want a method that will do for us this general forward Euler algorithm. So we do a function definition and call it forward Euler, for example. And directly think about the arguments. Of course, as we learned from the slides, we need some function, some right-hand side that goes in. So this is the right-hand side of the differential equation. Then we need a start value. Let's call this, no, I changed, it's okay. Let's call it y0, it's the starting value. And the parameters that we had. That were basically the ones that define the time interval. So we have some start value in time A, and we end at some time point B, and we do n steps in between. So this is our function definition. And later we want to return something that we don't know yet. We think about this now. For a starter, just return 0. So if you want to use it, you better write doc strings, and Spire is very helpful here. If you set the arguments already, then you get predefined doc strings. So the function is of type function. It's the right-hand side of the ODE. Right-hand side ODE. I do this quickly now. Of course, it's better to write good doc strings with all the details. Then we have, if it's multidimensional, an array of initial values. If it's only one ODE, then it's not an array, but in the general case, let's take it as an array. That's the start time. Oh, better goes into description. So this is a float start time, and we have, of course, a stop time is also a float. Of course, you don't have to write this. I just show you quickly that it's better to how to do this, and it's good to do this because otherwise later you don't know anymore what you meant with A and B. So this is the number of points in time. So it won't return an int. Instead, we will return, of course, the complete array. So the solution contains many points. So it will be an array. It's a solution to the ODE. So what do we have to do now in the forward Euler? Well, first we can come up with the step size. This we can calculate now from the time interval. So let's define some step size. You can call it h. And h is given by the width of the time interval divided by the number of steps. But we have, oh, this is fine. We just divide by n. But when we calculate the points in time, then we have to add 1. So what we then do is we predefine the array that we want to return. So y is supposed to be the solution of the ODE. So this will be some Numpy array, and we have to predefine it. For example, we can set zeros everywhere. And we have to do this in the correct size. The size we can deduce from the dimensions of the initial values. And the time steps we know, for many steps we do this. So in the rows, the dimensions of the initial values have to go, in the columns, the amount of time steps that we do. So we have an array of zeros, and we take the size of the initial value, gives us the number of rows, and then we need the number of time steps that we do, and this is now then n plus 1. And I always forget this. When you use ones or zeros, you have to put these dimensions in another pair of brackets. So this contains zeros for now, and we want to enter the solution here. This we need to calculate, of course. So first we know 1 point already because it's the initial value. You can set this one. So the first column of this array contains the initial value. It's the first step in time and is given. This is easy. We just set it. So we take all the rows in the first column, which is the zeros. And then we set the initial value that was given to us when we call the function. So this we can do. Now we have that, and now the interesting part comes. We want to calculate all the other values. So now we go back to the algorithm and check what we have to do. Okay, we take the step we had before, and to that we add the time step multiplied with the right-hand side evaluated at the step before. This means for us, we do this with a for loop for every step in time. So we have a for loop over the parameter k. And we do this n times from the first value on. The spider does the indentation automatically. And now the next step in time for all the dimensions that we have, for all the rows, next step in time is the kth plus once, or the k plus first step in time is given, as the algorithm stated, by the step in time that we had before, or the function evaluated there. We calculated this already in the step before. So the kth step, and from there we go along the tangent. We know the slope. We do one step in time, so we define the step size. So we can multiply h by the right-hand side, evaluated at the last position in time. The right-hand side was given to us as an argument. It's function or fun. So we evaluate the right-hand side fun now at the interesting points. That is k steps from where we started. We started at time point A and did k steps of size h. And also we have to send in the value that we've calculated before. So again, y evaluated at the point in time before. So that is at position k. So that should basically do it. And what we want to return then, of course, is y. So the complete solution. So this basically is the complete algorithm that we've seen here. So the general Euler, this one. And since we don't have much time left, I probably won't do everything by hand now, but instead show you a bit quicker how we proceed. So I basically prepared this here. This is again the forward Euler. As we just implemented it, is the method we know that we need for sure, the numerical strategy. And what we also need for sure is, of course, the right-hand side of the ODE. This is what we pass here as a function. That we need 2. And this we derive from the model that I showed you. There's a question in chat. I will check this in a second. So in this model here, we put the right-hand side for our system of ODEs. So as we learned, it contains, of course, the time and S and I, the right-hand side, and the parameters beta and gamma, the ones that we learned about. And we can basically directly return this right-hand side evaluated. Again, let's check the slides for the exact function. It was basically this. So the derivative of S was given by minus beta Si. This is put as the first dimension. So this is what you see here. As a first dimension in the list, we return minus beta Si. Beta here in the general version is now time dependent. And the second dimension is given by this rate with opposite sign. So beta times S times I. And we have to subtract gamma times I. So time derivative of S in the first dimension, time derivative of I in the second dimension in a list, and is sent to a Numpy array. So this is basically the right-hand side. And this is all the functions that we need. So let's check the chat. Okay, it's nothing, no question for me, something about the variable R. So, but no question. So in that case, I would proceed now. So what we have now is functions that we can use. So we can now write a main I've done this before because I expected that we will be short in time. And in our main, we put now all the exact parameters that we want to use and call all the functions and evaluate them. So what we do is we import again all the models that we need. We import Numpy, we import Matplotlib, and as I showed you, I went to the functions script I imported. Now, actually, this is functions too now. I wrote the two methods that I need. The right-hand side of the ODE, this is still general, and also the forward Euler. I can import this now. So basically, we wrote our own module. And now we set all the parameters that we want. So for example, we can say in our scenario, we use a time step of at least 1 day, probably a typical time unit should be 1 day, and we can model it for 100 days. So we start at day 0 and do this for 100 days. But let's evaluate it more often than once per day. So the number of time steps within the 100 days will be 10,000. So this is the number of time steps. Again, here we have start time and end time, for example, in days. Here I calculate now every discrete point in time by basically starting at time point A, taking the widths and counting up until we have the n+1 total points. Furthermore, we have to set the parameters. For example, the R value, let's assume this is given to us in some value for gamma and beta. I told you I set them constant as a beginning, but here I introduce them directly as lambda functions. I mean, now they are constant functions, but it doesn't matter. You can come up with a function still. So now it's easy to make them later in a not constant function. This you can do in the project, for example. Then let's come up with some initial values. We have to set them here. So, for example, we need some infected people for sure, so we can set it to 1% of the total amount of people they are infectious at the beginning, and the rest of the total amount of people is susceptible then. And no one has recovered at the beginning. And then we put this in the format that we want, because we have a set of ODEs. So both of them we stuff into an array now. And now we can send all these parameters into our right-hand side of the ODE. Therefore, I redefine now this as the CIR function, so that it depends only on time and the function that we're interested in, the solution of the IDE, because this is what our Euler method requires. The Euler method requires this format, right-hand side that depends on t and on time and the function itself that we're interested in. And by disguising the CIR general in this lambda function, we can send all the parameters before. Okay, now we can call the forward Euler with all the parameters that we have set and calculate a solution and hope that it works and plot the solution. So actually here no plotting is done so far. This was a plot that I had opened before. I just show it to you in the complete version, which basically contains these steps now, because there the plotting is done already. So here a few more lines are added, but they basically make the plot nice and so on. Apart from that, it's the same. we can again set all the values that we need. Here, for example, the R value is set to 2.5. So this is the incidence rate. So it models how many contacts people have in a given amount of time and how many get infected by this. And if it's too high, then the disease spreads quickly. So let's run it with this R value. And what we can see here is the solution for R set to 2.5. The dashed values are not interesting for us now. The not dashed curves are now the solution for S and for I, and you can see we start with basically everyone is susceptible and hardly anyone is infectious. And then the number of infectious people rises quickly while the number of healthy people drops until here you stay immune once you're immune until no one is left basically to get it. And the number of I goes down again. What you can see as a dashed line is a solver that I added, like not the method that we just implemented, but the solver that is available in NumPy. And as you can see, and actually in SciPy, as you can see, this solution differs from the one that we used because it's a better solver and because here I set the time steps very coarse. So for 100 days here, I used only 100 steps, but although we have this kind of, not so good approximation forward Euler, as we enter more steps, for example, 10,000 steps for this 100 days, this becomes way better. If I plot it again now, you cannot see a difference between the Euler method that we implemented and the original solver. So actually for enough points in time, it's not so bad. And it's easy to understand how it works. Yeah, you basically add this difference quotient and that's it. And for that, it's quite nice. Of course, many other options for a numerical strategy exist. This is just one way as a start. If you do the project, of course, you can come up with many other solvers. And what you also can do, of course, is now play around with the parameters. Someone asked, where do we get beta from? And I said, well, we assume someone gave it to us. Now we can check other scenarios. We can say, okay, the government said now there's a lockdown and let's have less contact. So maybe this rate is lower. We set better to lower value. People have less contact and infect less people. And then it looks totally different. If you set the R value to 1.1, then we can keep the amount of infected people low at every point in time. So hopefully the hospitals are not at their limits. And of course, if the other thing happens, if people have a lot of contact and infect many others, then it might happen that the numbers go up quickly, and at one point in time you have a lot of infected. So let's assume R is super high, like 5 or so. Then the solution looks like this. So if quick high peak of infected people, about half of the people available are sick at the same time or infectious at the same time. So this might cause problems at the hospital. I will send you all this material so you can play around for yourself, because unfortunately now we have to stop. And I think Stefan wanted to tell you about the project. I'll just check if he's here already. And the project deals exactly with this type of modeling. If you want to do this, you will receive more information about the modeling and also some ideas what you may want to try. So, but as far as I see, I think Stefan is not yet, he is here. So maybe he wants to say something now.
Okay, thank you. Yeah, I think now I'm allowed to talk. Thank you very much, Vanessa. So yeah, I guess there are some few minutes for questions afterwards. So yeah, I think Vanessa already said that there is the option for a follow-up project. So if you somehow liked this course and you're interested in continuing to program with Python, and in particular to work with this models of epidemiology, you are invited to participate. So we have set up a small project which you can do mainly independently, and we offer some support. So in fact, we have done this project within our own lecture here. This was a second semester lecture of mine, where we also gave a Python course in Konstanz here in Germany. And then in the end, the students had to do a program more or less as we have prepared it now for you. I'm not sure if I can share my screen. Then maybe I can.
Now you should be able to share.
Yeah. Can you see something?
Yes.
Okay, so this is more or less the sheet that we have prepared. So it's a 7-page sheet, and I think Vanessa has already shown several parts that are in here. It's basically explaining also these SIR model and some options. So we also want to deal with vaccinations, for example. And then also this forward Euler method to discretize ordinary differential equations. So as I said, we have set up this project for second semester students, so they do not really know yet how to solve ordinary differential equations. That's why there is a lot of explanation in this sheet. And yeah, in principle, this project is made for bachelor or master students. But yeah, in principle, everyone who is motivated is of course invited to participate. One objective of this is to get to know some motivated, good students from Peru. If you're interested to participate, this is probably the most important thing, then please write an email to myself. Here you find my email address. And before September 10, this would be the deadline, which is more or less in 2 weeks from now. And then the plan would be that we somehow set up a preliminary meeting. I think I put here beginning of October. And yeah, afterwards, the idea would be that you work more or less independently on the project. You're, of course, welcome to form groups and work on it together. We might hold some meeting somewhere in the middle, in December maybe, and then maybe in the very end, like February 2022, we plan to somehow hold a final meeting. And during this period, you can get support, of course, also from us. You would need to contact us. So I think the first person to contact would be Vanessa. So what is important also is that we will not be able to issue a certificate for that. So because the work will mainly be self-independent. So it's really for people that are motivated to learn something, but unfortunately you cannot get any certificate here. And I can just scroll briefly through this project. So I think Vanessa has explained this first part, like the SIR model. I've also seen that in this conference, there are a lot of talks about epidemiology. So many of you will be very familiar with this. Then I think we also have the SEIR model. I don't know if Vanessa has explained that as well. Here we add an additional exposed group E, which is an incubation period. And then we also add some vaccination to the model. And then we have this model in principle, and we want to implement this. We will play around with different parameters. We will somehow analyze the equations and do many different things around this. We will analyze, for example, a simple lockdown strategy. And you find the exercises here in the end, at page 6 of 7. There are 9 exercises, which are more or less the exercises that our students had to solve. You are of course invited to also come up with your own exercises. You do not have to stick one by one to these exercises. This is just to somehow give you an idea what you could do. Okay, so the important thing I think is this deadline, September 10. Please write me an email until then with some few informations like your status, if you're a bachelor student in mathematics or whatever, and maybe your university, such that we more or less know who will participate. Okay, and if you have any questions, you can contact us also at any time. I think we will upload this file as well with all the material that Vanessa uploads. I don't know, maybe you can share the link again, or we write it by mail.
Yes, I can share it again. So I hope everyone received the first email. I sent it to everyone on the participants list. And this leads to a folder on the cloud. So all the material, also the things that I showed you just recently now in Spider, all these files I will put there. So you have a first glimpse of how to do this and can play around with it, because we hadn't the time to do everything now in detail, but you can just play around with these files and add your own code. And also the slides I can send you and the Jupyter notebooks. And yeah, it's the same link that you received, but maybe just to make sure that everyone has it, I can just send another email. Otherwise, check the same cloud folder. Everything will end up there.
Okay, yeah, I think it's a good idea to send another email that everyone has all the information. I think there will be a plenary talk starting in some minutes, but we can use this, I don't know, 2 or 3 minutes. If you have any questions, either questions to Vanessa for the course or regarding the project. So please feel free to ask.
So there was one question where to find the material. Well, that is in the cloud. I will send the link again via email. If you're not on the participants list, if you haven't received an email like this week, so I think on Monday or Tuesday, then probably have to contact the organization committee again to be put on the list, or otherwise you just send me now with direct message your email. I can add you, because most of the, I think it were 200 people, so most of you should be on the list, and who's not on it can send me a message now.
Okay, so I think there are no further questions at the moment. So if you have any questions, feel free to contact us via email, both concerning this Python course and both concerning also concerning the projects. Okay, so I'm not sure if we should already go to the plenary talk. Maybe one of the organizers can tell us if we already switch over to Thomas Wick's talk. Continuamos con la plenaria de Thomas Wick.
So apparently he tries to talk, but he's not a host yet.
Ah, okay.
But yes, I don't think that we can do anything. I think that we're only co-hosts, so the host has to give the rights. But I think
now I can speak.
More questions. So, but thank you again, muchas gracias for participating. And then maybe if you have questions, just contact us. So, bye, and have fun now with Thomas.
Okay, so thank you very much, Vanessa. So then I'm the one who is in charge to also introduce Thomas Wick. So I think it's time for the plenary. We continue also in English, I guess. So Thomas Wick got his PhD. Professor Thomas Wick got his PhD in Heidelberg in 2011, where he worked on fluid structure interactions. Then afterwards, he moved around almost the whole world and worked in very different places where he gained a lot of experience. So one place was Austin, Texas, where he worked at ISIS with Professor Mary Wheeler for at least 2 years. There he also started working on fracture propagation, which I think will be the main topic of today's talk.